Welcome to the series of e-learning modules on geometric mean. In this module, we are going to cover the definition and calculation of geometric mean for the various statistical series, followed by its application, advantages, and limitations. By the end of this session, you will be able to explain the concept of geometric mean, calculation of geometric mean for statistical series, application of geometric mean, properties of geometric mean. First, we shall have a look at the definition of a mean. Means are mathematical formulations used to characterize the central tendency of a set of numbers. Most people are familiar with the arithmetic mean, which is also commonly called an average. Geometric mean has specific utility in the field of science, finance, and statistics. Geometric mean is the nth root of the product of n items of a series. For example, if there are 2 or 3 items in a series, then the square root or the cube root of the products of the item in the series is taken. A geometric mean is denoted by the alphabet G or as Gm. Symbolically, it is shown as G is equal to the nth root of the variables x1 into x2 into x3 and so on to xn. Let us take an example of a series having 3 items, 4, 6 and 9, and find their geometric mean. In this case, the geometric mean G is equal to the cube root of the products of the variables 4, 6 and 9, which is equal to the cube root of 216, which is equal to 6. Whenever the number of items in the series are 2 or 3, it is easy to take out the roots and calculate the geometric mean. But when there are more items in the series, then it is excessively difficult finding the roots of the items. To simplify, we use the logarithms for calculation. The average of the logarithmic value of a data set converted back to a base 10 number. That is, the log of the geometric mean is equal to the log of the variables x1 plus x2 plus x3 plus and also to plus xn divided by the number of the data n, or log of the geometric mean is equal to the sigma of log x divided by n. Thus, by removing the log, we get that the geometric mean is equal to the antilog of sigma log x divided by n. In statistics, we classify the data using various statistical series. Statistical series are classified into individual series, discrete series, and continuous series. We have seen that averages can be calculated differently for various types of series. Similarly, the geometric mean can be calculated for 3 different types of series. In the section that follows, we shall discuss the calculation of geometric mean for these 3 types of series. First, we shall look at the computation of geometric mean for individual or ungrouped data. An individual or ungrouped data is a data where all the values are shown separately and is called an individual series. Suppose an individual series contains n items as x1, x2, x3 and so on to xn. Then the geometric mean G is defined as geometric mean is equal to 1 by n to the power of the variables. Taking logarithm on both sides of the equation, we get log of geometric mean is equal to log 1 divided by n multiplied by log of x1 plus log of x2 plus log of x3 plus so on to log of xn, which is equal to the total value of the logarithm of x variable divided by n. Thus, the geometric mean is equal to antilog of the total value of the logarithm of x variables divided by n. Here is a look at the steps in the calculation of geometric mean for individual or ungrouped data. Take the logarithms of the variables x. Obtain the total of the logarithm sigma of log x. Divide sigma of log x by n. Take the antilog of the value obtained in the previous step. This gives the value of the geometric mean. Let us take a few examples to understand the computation of geometric mean in an individual series. In the first example, we are given that the annual rate of growth for a factory for 5 years as 7%, 8%, 4%, 6%, and 10% respectively. We have to calculate the average rate of the growth per annum for this period. Now, if the growth for the company is 100 in the beginning, then in the 5 years, the growth is given as 100 plus 7, 100 plus 8, 100 plus 4, 100 plus 6, and 100 plus 10 respectively. We create a table where the first column of the table we take the year, and in the second column we have taken 100 as the beginning growth and added the percentage increase in the growth. The third column is the logarithm value of the variables, and the total of the log of the values is equal to 1014654. We shall now calculate the geometric mean using the formula for geometric mean. Substituting the values, we get geometric mean is equal to the antilog of the total of logarithm of the x variables, that is 10.14654 in this case, divided by 5, the total number of the data, which is equal to antilog of 2.0293, which is equal to 106.98. Thus, the average rate growth is 106.98 minus 100, which is equal to 6.98. And therefore, we can say that the average rate of growth percentage per annum is 6.98%. In the second example, we are given the daily income of 10 families of a particular place of which we need to calculate the geometric mean. The values given are 85, 70, 15, 75, 500, 8, 45, 250, 40, and 36. So first, we create a table with the number of families in the first column and the income, the x variables in the second column. The third column represents the logarithm value of the x variable, the total of which is 17.6373. Applying the formulae, we get that the geometric mean is equal to the antilog of the total logarithmic value of the variables divided by the number of the data, that is 17.6373 divided by 10, which is equal to antilog of 1.7637, which is equal to 58.03. Next, we shall look at the computation of the second series of geometric mean for discrete frequency distribution. A discrete frequency distribution is a statistical series which represents the variables in the data and the number of time each variable as occurred. Here, while calculating the geometric mean, we need to consider both the variable x and frequency f of the data. Suppose there is a discrete frequency distribution with x1, x2 and so on to xn, with data having frequencies f1, f2 and so on to fn respectively. Then the geometric mean is the root of the product of the frequency with the variable. In this case, the frequencies are f1, f2 and so on to fn, and the variables are x1, x2 and so on to xn. Taking logarithms on both sides of the equation, we get log of the geometric mean is equal to 1 by n of frequency and its product of the log of the variables. The logarithm of the geometric mean is equal to 1 by n into the sigma or total of the product of the frequency with the logarithm value of x variable divided by n. Thus, by removing the log from the left side of the equation, we get geometric mean is equal to antilog of the sigma or total of the product of the frequency with the logarithm value of the x variable divided by n. Steps. Find the logarithms of the variable x. Multiply these logarithms with the respective frequencies. Obtain the total of summation of f log x. Divide summation of f log x by n, which is the total of frequency. Take the antilog of the value so obtained. This gives the value of the geometric mean. Let us take a few examples to understand the computation of geometric mean in a discrete frequency distribution series. In the first example, we are required to calculate the geometric mean from the data given in a table consisting of the wages and the number of people receiving the corresponding wages. First step, find the logarithms of the x variable as shown in the table. The log of the variable's wages 20 is equal to 1.3010, 30 is 1.4771 and so on. Multiply the log with the frequency, that is, when we multiply 1.3010, the log value of the variable with the frequency 5, we get 6.5051. Similarly, the values for the other variables are calculated. We also find the total of the product, that is 49.7954. Calculate the geometric mean by applying the formulae. We get that the geometric mean is equal to antilog of the sigma or total of the product of the frequency with the logarithm value of x variable divided by n, which is equal to antilog of 49.7954 divided by 30, which is again equal to antilog of 1.65985, which is equal to 45.69 as the geometric mean. In the second example, we are required to calculate the geometric mean from the discrete frequency distribution table given. Finding the logarithms of the age as the x variable, we get the log of 5 as 0.6990, for 10 as 1.0000, and so on for the other variables as shown in the table. In step 2, we multiply the logarithms with the frequency. That is, m in this case, we multiply the log value 0.6990 with 12, which is the frequency, and get 8.3876 and so on for the other variables, Then the total of the product is taken, that is 125.5482 in this case, along with the total of the frequency n, which is equal to 100. Calculation of GM by applying the formula, we get that the geometric mean is equal to the antilog of the sigma or the total of the product of the frequency with the logarithm value of the x variable divided by n, which is equal to the antilog of 125.5482 divided by 100, which is equal to antilog 1.25548, which gives the geometric mean equal to 18.009. We shall now look at the computation of geometric mean for continuous frequency distribution. A continuous frequency distribution data does not assume exact value, but is given only within a certain range, and the number of data points in that range is mentioned. Here, while calculating the geometric mean, we need to consider the mid-value m of the range variable x and frequency f of the data. We now need to look at the steps involved in the computation of geometric mean for a continuous frequency distribution. Find the mid-values of the classes. Take the logarithms of the mid-value n. Multiply these logarithms with the respective frequencies. Obtain the total of summation of f log m. Divide summation of f log m by n, total of frequency. Take the antilog of the value so obtained. This gives the value of the geometric mean. Therefore, geometric mean is equal to the sigma or total of the product of the frequency with the logarithm value of the x variable divided by n. Let us take a few examples to understand the computation of geometric mean in a continuous frequency distribution series. In the first example, we shall compute the geometric mean for the data given in the table as shown. The table contains marks in the series with class intervals of 4 as 4 to 6, 8 to 12, 12 to 16, 16 to 20, and so on, and the respective frequencies are given as 6, 10, 18, 30, 15, and so on. In the solution, first let us find the mid-value of the given classes and then calculate the logarithms. The mid-value in this example is calculated by taking the class interval. Say for the interval 4 to 8, we add the upper limit and the lower limit, that is 4 plus 8, which is 12, divided by 2 to take the average, which is 6, the midpoint. Similarly, we calculate the mid-values of all the class intervals as shown in the table. Then, the logarithmic value of the midpoint values are taken. In this case, the logarithmic value of 6 is 0.7782, which is further multiplied with the frequency 6, which is equal to 4.66891. The same method is followed for the other values as represented in the table. Now, the calculation of geometric mean is done by using the formulae, that is, geometric mean is equal to the antilog of the sigma or total of the product of the frequency with the logarithm value of the x variable divided by n. In this case, the geometric mean is equal to antilog of 137.19306 divided by 109, which is equal to antilog of 1.25865. Thus, the geometric mean is equal to 18.14. In the next example here, the table contains two columns. one containing the class interval of marks and the other with the number of students in each class. From this data, we have to calculate the geometric mean. The class interval given for this is 10. So the ranges in the marks table will be 0 to 10, 10 to 20, 20 to 30, 30 to 40, and so on. The corresponding values of number of students are given as 5, 10, 25, 30, 20, and 10 respectively. The first step here is the calculation of mid-value and logarithms. Here, we shall find the mid-value of the classes and then calculate the logarithms of the mid-values. In this example, when we calculate, we take the class interval 0 to 10 and then add the upper limit and the lower limit, that is 0 plus 10, which is equal to 10, divided by 2 to take the average. We get 5. Similarly, we calculate the mid-values of all the class intervals as shown in the table. Then, the logarithmic value of these midpoint values are taken. In this case, the logarithmic value of 5 is 0.6990, which is further multiplied with the frequency 5, which is equal to 145.23327. The same method is followed for the other values as represented in the table. Calculation of geometric mean is done by using the formulae, that is, the geometric mean is equal to the antilog of the sigma, or total of the product of the frequency with the logarithm value of the x variable divided by n. In this case, the geometric mean is equal to the antilog of 145.23327 divided by 100, which is equal to antilog of 1.45233. Thus, the geometric mean is equal to 28.34. We will now look at the formulae for computing compound interest. In business and economic problems, very often we are faced with the questions pertaining to percentage rates change over time. The most generally useful interpretation of this term is a constant percentage rate of change, which if applied each year would take us from the first to the last figure. The correct answer can be obtained through the use of geometric mean, or what amounts to the same thing through the use of the compound interest calculations. In this discussion, the relationship between the average and the compound interest calculation is indicated. The compound interest formula is expressed as P-n is equal to P-O multiplied by 1 plus R whole number n, where P-n is the amount accumulated at the end of n periods. P-O is the original principal. R is the rate of interest expressed as a decimal, and n is the number of compounding periods. It follows from the above formula that rate of interest is equal to the n root of the amount accumulated at the end of n period divided by original principal minus 1. If interest is compounded at different rates in each time period, and if these successive rates are denoted by R1, R2, and so on to Rn, then the amount accumulated at the end of n periods with an original principal of P-O is calculated as P-n is equal to P-O into 1 plus R1 into 1 plus R2 plus and so on to 1 plus Rn. We shall now look at the application of geometric mean. The geometric mean is used to find the average percentage increase in sales, production, population, or other economic or business series. The geometric mean is a useful average for measuring the growth of the population because population increases in geometric progression. The geometric mean is considered to be the best average in the construction of index numbers. The geometric mean is the most suitable when large weights have to be given to small items and small weights to large items for situations we usually face in economic and social fields. Here is an example to illustrate the use of geometric mean. In a garment factory, the overhead expenses went up by 32% as compared to the previous year. This increased by 40% the next year and by 50% the following year. Calculate the average rate of increase in the overhead expenses over the 3 years. We know that in average ratios and percentages, geometric mean is more appropriate. Hence, applying geometric mean here. If the growth of the company is 100 in the beginning, then in the 3 years, the growth is given as follows. That is, in the first column of the table, we take the year, and in the second column, we have taken 100 as the beginning growth and added the percentage increase in the growth. The third column is the logarithm value of the variables and the total of the logarithm of the values, which is equal to 6.4428. We will now calculate the geometric mean using the formula. That is, the geometric mean is equal to the antilog of the total of logarithm of the x variable, that is 6.4428 in this case, divided by 3, the total number of data, which is equal to antilog of 2.1476, which is equal to 140.5. Therefore, the average rate of increase in the overhead expenses is equal to 140.5 minus 100, which is equal to 40.5%. Combined geometric mean. As we calculate the combined arithmetic mean, we can also calculate the geometric mean for items having a number of sets in them. If the geometric mean of n items is 6, and then these n items are divided into sets, first containing n1 items and second containing n2 items, having g1 and g2 as their respective geometric mean. Then, the logarithm value is taken on both sides of the equation, that is, the log of the geometric mean is equal to the product of the number of items and the log of the geometric mean divided by the total number of items. To understand the above equation, let us take an example. In this example, we have two sets, n1 with 5 items having a geometric mean 20 and n2 with 10 items having geometric mean 35.28. Find the respective geometric mean. By applying the formula and substituting the given values, that is, n1 as 5, n2 as 10, g1 is equal to 20 and g2 is 35.28. We find the GM of the entire series n. N is equal to the total of n1 plus n2. Substituting the values in the equation and simplifying, we get the log of the geometric mean as 1.465, and when we find the geometric mean, we get the value as 29.17, which is the antilog of 1.465. Corrected geometric mean is used when there is a mistake in the observations while calculating the geometric mean. We use the following formula to apply the correction. The correct geometric mean is equal to the product of the geometric mean of the observation and the correct observation divided by the wrong observation to the power of 1 by n. Here is an example. The geometric mean of 10 observations was calculated as 28.6. It was later discovered that one of the observations was recorded as 23.4 instead of 32.4. We have to apply the correction and recalculate the correct geometric mean. So, we know that n is equal to 10. Calculated GM is 28.6. Correct observation is 32.4 and wrong observation recorded was 23.4. Substituting the values in the equation, we get correct geometric mean is equal to the product of the geometric mean 28.6 and the correct value 32.4 divided by the wrong observation 23.4 to the power of 1 by 10. Taking log on both sides of the equation and calculating, we will get the logarithmic value of geometric mean as 1.47053. Thus, the geometric mean is equal to antilog of 1.47053, which is equal to 29.54. Properties of geometric mean. There are two important mathematical properties of geometric mean. Property 1. The product of the value of the series will remain unchanged when the value of geometric mean is substituted for each value. Property 2. The sum of the deviations of the logarithms of the original observations above or below the logarithm of the geometric mean is equal. This also means that the value of the geometric mean is such as to balance the ratio deviations of the observations from it. Here, to illustrate the first property, we shall take an example. Here we have to find the geometric mean for series 2, 4 and 8. Using the formula for GM, GM is equal to cube root of 2 into 4 into 8, which is equal to cube root of 64, which is 4. When substituting the mean value in the series, we get the same value series. That is 4 into 4 into 4, which will be 64. To illustrate the second property, here is an example. If 4 by 2 into 4 by 4 is equal to 2, which can also be represented as 8 by 4, this property is useful as it is adapted in calculating the average ratios, rates of change and logarithmically distributed series. Here is a summary of our learning in this session. In this session, we have understood the concept of geometric mean. The calculation of geometric mean for various statistical series. Properties and application of geometric mean.